Hello, my stormwater management class. So, this recorded lecture is for this Friday, and this will be the topic of this lecture will be urban stormwater pollution, which is chapter 8 from your textbook. So, for this one, the main learning objective is how can you model the urban stormwater quality, okay, not the quantity. So till now we always discussed about the quantity, so this is kind of like second part where we will do the quality modeling. Now what do we mean by quality modeling? By quality modeling we usually mean that like annually how much pollutants you can get from any watershed. Okay, so when I say pollutant, it can be different types of pollutant, which I will discuss shortly. So that is the learning objective for this lesson. Okay, so as I was saying, we will work with the quality purpose, like account for any stormwater management devices. So before we discuss about the devices, we need to know how can we find out the total amount of different pollutants, and then we can design something which will control this amount of pollutants to improve the water quality, runoff quality. Okay, so there are basically two steps. The first one is like right after the rainfall till the next rainfall. In between this time, like during this dry period, there can be different types of pollutant buildup. Okay, and that is the first step. Like at first the pollutants needs to be built up, and the second one is because of the rain this pollutant will be washed off. Okay, so those are the two steps, and when the pollutants get washed off, usually they discharge quickly into the drainage system, and ultimately they end up with the receiving water or the natural stream. So that's why it is very important that we find out what is the total amount of pollutant, so that it will not affect the natural stream. Okay, so that's what we need to do. Now there are different types of pollutant based on from where those pollutants are coming. So mostly it's the total suspended solid, which is the primary indicator of stormwater pollution. So total suspended solid is like different particles which is like suspended, and it will take some time to settle those. Sometimes it will require some chemical treatment as well. Okay, mostly nutrients, mostly phosphorus and nitrogen. Those are basically coming from pesticides or something like that, which you apply for plant growth or something like that. It can be some organic carbon, it can be trace metals like cadmium, copper, zinc from automobiles, gutter and building material, because water actually flowing over the building roof or the car, or from parking lot you can see like there can be different types of oil as well. So those are different types of pollutants. We need to find out what will be the total amount of pollutants. Okay, so since the objective of this lesson is urban stormwater quality, we need to know what are the different options we have. So there are basically two options. The first one is the lump ton modeling, which is like we will find out what will be the total pollution load in kilogram or pound over a period of time, like month or year, something like that. Another one is the continuous time modeling. Basically the main difference between these one is like it will estimate the pollutant concentration over time generated from watershed during a particular storm event or a series of storm event. So basically in between two storms, okay, what is the total pollutants we can have. And for this one we have these two steps which you already discussed a little bit. Like at first there will be one step where all the pollutant will be built up, and then because of that rainfall all of this pollutant will be washed off. Okay, now TSS, which is the total suspended solid, that is the primary indicator of pollution. Now the question is, okay, then what about the other pollutants like all the trace metal or the hydrocarbon or carbon? So usually the other pollutants, they have kind of a constant ratio with the suspended solid for a given type of land use. So if we know the land use and land type and the rainfall type, and if we can find the total suspended solid amount, we can kind of like using that ratio, constant ratio, we can find okay what will be the amount of other type of pollutants as well. Okay, so since our very first step is like pollutant buildup, there can be two types of buildup, like two mechanism of buildup based on what type of surface we have. Just think about that. The impervious surface, like any concrete floor or the pavement, something like that, they are not able to take that much of water. So and it is kind of like you will not think about like accumulating of concrete or asphalt over the road, like from a road. So what I'm saying that the surface is kind of permanent, so all the pollutants, like they're coming from some other places because of the wind and everything. So here for impervious surface, that is the equation, and most of the time it's actually like the empirical equation. There are multiple equations here, so I just listed few of those so that U naught is the weight of solid buildups in pound per unit area prior to a rain. Time elapsed in the last storm in days, because we are actually calculating the solids buildup in between two rains. Okay, and there are a few feeding parameters as well, because those are empirical equation. And once we find out that solid buildup, then the next one is total weight of solids available for wash off. Okay, again those are some there are some constant. Now one thing, the solids wash off is usually characterized by exponential decay function of the form, which simply says that initially the rate of wash off will be very high, obviously that's right after the rainfall, and eventually it will be kind of like constant. Okay, or like it will reduce and it will become constant. So delta P is actually the one which is the load, and for solid wash off and solid build off, there are two things which is very very important, which is the average concentration of the pollutants. Like this one is weight over volume, and this one is weight over time, which is the pollutant load rate. And these are very important to determine, because that will help like you can kind of route from upstream to downstream, what will be the concentration, what will be the pollutant rate at different points. So this one is important. Okay, for pervious surface, whenever we say solids wash off, basically we are saying kind of like what will be the erosion. Okay, because pervious surface, they don't have any like fixed or strong surface, like immovable surface. That is actually the movable surface. So whenever there is a rainfall, if there will be some sort of erosion if there is no cover or something like that. So basically when we try to find solids wash off, that is actually the soil loss equation. Okay, and this delta P is weight of the solid in pounds contained in the stormwater runoff during delta T. Now if we look at different parameters, we will understand why for pervious surface we actually use the erosion equation. Okay, so just think about that. What are the factors which can affect the erosion? The very first thing is, what is the area? If the area is big, obviously the erosion will be big. The rainfall factor, like is it 5 years rainfall, it is 10 years rainfall, what is the amount or magnitude, something like that, what is the duration of rainfall. So R is actually for that. K is soil erodibility factors in tons or acre. So erodibility factor means what type of soil we have in the watershed, what is the organic matter content, something like that. So if you look at this table, you will kind of understand that how the K is varying. Okay, LS, slope length gradient ratio, that is simply saying if the watershed, if it's like too steep, obviously it will take more soil with the water flow. Okay, so that is important. What is the slope length ratio? C is cropping management factor. Cropping management factor is whether there is a grass or any type of plantation there, so that is the C. And the PF is erosion control practice factor. It's like are you adding anything for the erosion control, any type of measurement, any type of something, so that is actually the PF. And so for each one we have some table, we have some ways to find these values, and once we get that, we can actually find out what will be the solids wash off for the pervious surface. Okay, so we discussed that R, like based on return period, based on location, what will be that. So this one is if you know the location, but if we don't know the location, this will be the one. We can actually use this kind of empirical one, and if we know the location, we can directly use the table. Okay, so slope length ratio LS is, that's how you can find out that. So L is overland flow length in feet from the point of origin of the overland flow to the point runoff enters a defined channel like a gutter or an inlet. Okay, and the S is average surface slope over the given runoff length, feet over feet. Cropping management factor C, it's 1 for the bare soil, then like there is nothing. 0.003, 90% of grass cover. 0.001 canopy cover, like the if there is any plantation which will kind of work as a canopy over that watershed. If it's 100%, the cropping management factor is very low, 0.001, but instead of 100, if you have 20, it will increase. So basically bare soil is the maximum one because there is nothing. Okay, and erosion control practice for the urban areas, usually most of the time it's PF equals to 1. Okay, so class example 27 is something, how can you find out what will be the total suspended solid from watershed. I will work on class example 27 and 28 in a separate video. Okay, so the next part, not next part, as part of this one, there are two more things like pollutographs and the lodographs. So those are kind of hydrograph, okay, for pollutant loading. Okay, so that will kind of tell you like with time how the loading and how the loading factor and the pollutant factor, like those are actually changing over the time. So the lodograph is a plot of load rates versus time, W over Q. Okay, and okay, and the pollutograph is something like pollutant concentration over the time. So those are two things. And just like the hydrograph, like hydrograph will tell you what will be the magnitude of in runoff at different point in a channel, this pollutograph and lodograph can tell you what will be the concentration and load rates at different points on that natural stream. So using that Muskingum routing method, we can use the same method and we can do the routing. I'm not going into that much details, but I would like to show you one example from your textbook, which is example 8.3. What they did from the upstream, they actually found out what will be the concentration and load at the downstream at different points, and you can see that was the Q, that was the W, that was the C. Okay, so that one is the lodograph, this one is the pollutograph, and you can see that with time how they are varying in between downstream and upstream. Okay, so the very final thing is like if we want to find out the total load, like annual pollutant load for different type of storm sewer, how can we find out that? So since there are basically two types of sewer system for carrying the runoff. The first one is separate storm sewer, and the second one is combined storm sewer. Okay, so when we say combined storm sewer, that is actually carrying runoff in the sewage. Okay, so that is something that's why it's called combined, and the separate one is for sewage and runoff. They have two separate system. So without knowing too much details, you kind of tell the combined storm sewer will obviously have more pollutants, because it will not only carry the runoff, the pollutant from the runoff, it will also carry some other pollutants from other type of household waste or some other type of waste as well. Okay, so the EPA model, EPL, which is Environmental Protection Agency, they came up with this one for separate storm sewer, and there is one more equation for combined storm sewer. Okay, so M is the pound of pollutant generated per acre of land per year. Alpha is pollutant loading factor. You can see from here for different types of land use, for different types of pollutants, what will be that. P is the annual precipitation in inch. F is the population density function, because obviously that is important. And S is street sweeping factor, like how frequently you are getting rainfall or something. So that will actually tell you how frequently that wash off is happening. Okay, so this one is again like N depends on the sweeping interval NS. If the NS is 20 days, S equal to 1, and the NS is if the less than 20 days, that's how you will find. F depends on the land use. So for different types of land use, the F will be something. For residential area, population density is very important. For school and commercial industrial areas, that is kind of fixed. Okay, and for combined sewer, kind of same factor, but if you notice, just notice one thing. For residential BOD5 it's 3.29, and here it's 0.799. so you can tell that for the combined one, obviously the pollutant load will be higher than the separate storm sewer. Okay, how can you, they also give you the approximation, like how can you find out the annual runoff estimation to estimate the average pollutant concentration. These are some equation. If you don't know the runoff directly, that's how you can do that. Like from rainfall, 20% will be the initial abstraction, and you need to find out the depression storage, and once you know that, you can actually find out the runoff. Most of the time we will have the runoff. Okay, so that is the class example 28. So as I said earlier, I will make a different video for the class example 27 and 28. Okay, thank you class.